Okay, so let's have a look at the structure of an atom, and our go-to place is always the periodic table. The big number with the element is the mass number, and I remember it because if I get onto the scale, it's a big number. And the atomic mass, that's the number that is unique to that element, just like your passport number is unique to you. So the atomic number tells me the number of protons in the atom, and it's unique to that element. And because in an atom, the positive protons equals the number of negative electrons, if I've got 3 protons, I'm going to have 3 electrons. Now, the mass number, if that includes the particles that have got a decent mass, the protons and the neutrons, remember the electrons are so small that they are negligible. We don't count the mass. So if 3 of those 7 are protons, then the neutrons, if we go 7 minus 3, that gives me 4 neutrons. Now, if you remember, the protons and the neutrons go in the nucleus of the atom, which is over there, and the electrons go in the orbitals or the shells. Now, remember the rule. You fill 2 in the first shell. Once that's filled, you go to the next shell, and that needs to be filled with 8 before you go to the next shell, which also needs to be filled with 8. So the electron configuration of lithium is 2 in the first shell, comma, 1 in the last shell. Now, because it's got 1 electron in the outer shell, it's the clue that it's in which group? You're right, group 1. And because it's got 2 shells, what period or row is it on the periodic table? Row 2. Well done. Okay, so that's that all written over there. Remember, PEN, protons, electrons, and neutrons. Nice simple question, and there'll be something in the quiz on this. Now, isotopes. Isotopes. I could have lithium in the form of 8,3 or 6,3. Those are called isotopes. Now, what's happening is it's still lithium because it's still got an atomic number of 3, but because this number is changing, it's telling me that there are a different number of neutrons. That's important. Isotopes, it's because there's a different number of neutrons, so the mass number is different. Okay, how do I work out the relative mass of the substance? Now, what I do is I use my periodic table. Funny that, coming in useful again. So, for example, on my periodic table, the atomic mass of calcium in calcium carbonate is 40. I've got 1 atom of calcium, so it's 40, plus the relative mass of carbon is 12 on my periodic table, and the relative mass of oxygen is 16, but I've got 3 atoms of oxygen, so it's 16 times 3, which gives me 100. So you see why the previous video was useful. Lots of people kind of go, oh, I don't know what to do, because they forget that it's all on your periodic table. Okay? Right, now I've added this in because this is the first calculation, big calculation in the first couple of sections that you did in Year 9, and in the last Year 9 test, everybody, almost everybody, forgot how to do this. So I don't want you to be like that. This formula. If I've got different isotopes and I want to work out what is the relative atomic mass for that element, I get told what percentage of the isotope I have in a mixture, and of course what the relative mass is, and the percentage of the other isotope in the mixture, and I divide it by the total abundance. So if I've got 6 grams of one and 4 grams of the other, that would be 10. Or if I've got a percentage, the total abundance will of course be 100. So let's look at a worked example. This is the formula you've got to have on your well-stuck sticky note in your brain. This is an example. So a sample of chlorine contains 75% of chlorine 35 and 25% of chlorine 37. So writing out the formula, I can substitute in. I have 75% multiplied by the relative mass of chlorine, which is 35, plus, and sorry, I should have put brackets here, 25% of chlorine 37. So I multiply that and I add it to the multiplication of that, and I've got a total of 100. So I get 3,550 divided by 100 gives me an answer of 35.5, and that's why in your periodic table chlorine unusually has a decimal place, because it is the average. Okay, and this is how they worked it out. Conservation of mass, super duper easy, just like electricity. Mass isn't created or destroyed, it's just changed in different forms. So the mass of the reactants, if I had 200 grams in total of reactants, I'm going to get 200 gram in total of products. Okay, as long as I've got a closed system. So closed system means, like in this diagram here with the crucible, I've got a lid on, so when the magnesium reacts with oxygen in the air, nothing can escape. Okay, that's what a closed system means, because if I have a gas that's escaping, of course the product mass inside there is going to be less. Moles, we love moles. Okay, a mole of a substance is the relative formula mass of that substance in grams. What does that mean? Simply this. If I want to know how much a mole of sodium is, it's 23 grams. If I want to know how much a mole of carbon dioxide is, if I work out the relative formula mass of carbon dioxide, it's 44. A mole of carbon dioxide will weigh or have a mass of 44 grams. Okay, that's simple. Now, Avogadro's rule. Now, this always reminds me, if I go to the bakery and ask for a dozen donuts, they always give me 12 donuts. A mole, this beautiful stargaze mole, it's got nothing to do with a chemistry mole. A mole refers to the number of particles in a mole of substances. So just like, you know, it's 12 for a dozen, for a mole, you've got 6.02 times 10 to the 23 molecules in 1 mole of a substance. Okay, so it doesn't matter whether I've got molecules, ions, particles, or atoms, it's always that same number for a mole. So 1 mole of sodium contains 6.02 times 10 to the 23 particles. 2 moles of sodium contains double that. Okay, nice and easy. Something interesting about that big number. If I covered the whole of South Africa in a mole of Smarties, it would come a meter high. It's a bonkers number. Okay, right. And there I've got another example. 1 mole of carbon dioxide contains 6.02 times 10 to the 23 particles. If it was double that, it'd be double the number of particles. Okay, simple. Now we love adding questions about calculating the number of moles in a substance. So rather than writing out moles all the time, I can just use the letter N, and I can refer to it as the amount of substance. And that's why if you really mean volume and not moles, then you must say volume rather than amount, because amount and moles are the same thing. Okay, and the unit is moles, and it's abbreviated to MOL without the E. So this is the formula. The number of moles is the mass of the substance divided by the relative mass, the relative atomic mass if it's an element, relative molecular mass if it's a compound. Okay, and if you like using your triangles, I always go my naughty mother, okay, with the mass, the number of moles, and the relative mass. If I cover up the N, I'm left with mass divided by the relative mass. So let's have a look at example. How many moles are there in 8 grams of copper 2 oxide? So I've been given the formula. The 2 just tells me I'm dealing with copper 2 plus rather than copper 1 plus. What have I got? Now this is where your highlighter comes in handy. I've got a mass, and because I've got the formula, I've got a periodic table, so you're right, you can work out the relative mass. So writing down the formula so that Mrs. Gale and Mr. Gregson don't come and virtually throttle you. N equals M over MR equals the mass. The actual mass is 8 gram. The relative mass of copper oxide is 64 plus 16, which gives me 80. So it's 8 divided by 80 is 0.01. Don't forget your units. 0.1 moles. That's simple. You can do it. I know you can. Okay, empirical formula. This is a biggie, but I've got a recipe for you. So if I simply say, what is the empirical formula? Your answer is it's the simplest ratio of atoms. So C6H12O6, which is glucose. If I simplify it, I can divide everything by 6, so I get C1H2O1. That's simple. But they like to complicate things. So if they want you to work out the empirical formula from a certain mass or a percentage from an element, these are the steps that you need to use. And I'm afraid the only way is to learn this recipe off by heart. Okay? It's easier if I show you with a worked example. So this is what the question will look like. Find the simplest formula of an oxide of iron formed by 2.24 grams of iron with 0.96 grams of oxygen. And they give you the numbers from the periodic table. So in my two columns, I know I've got iron and I know that I have got oxygen. Okay, I've got iron and I've got oxygen. The percentage, if they give it to you as a percentage, you put that over there. Or if they give you it as a mass, you just put it over there. So I've got 2.24 grams of iron and 0.96 grams of oxygen. The other bit of information that I've got, because I've got a periodic table, my go-to place, oxygen has a relative mass of, iron has a relative mass of 56 and oxygen has a mass of 16. So now I've got the mass and the relative mass, I can do my mole calculation. So my naughty mother, M over MR is 0.04 and 0.96 divided by 16 is 0.06. Now this is the unusual bit. I look at these two numbers and out of these I say which one is the smallest, and obviously 0.04 is the smallest. So now I'm going to divide both of these by 0.04. So 0.4 divided by 0.4 is 1 and 0.6 divided by 0.4 is 1.5. Now, because this isn't a whole number, I want to make it a whole number because we don't have half an atom. So what I'm going to do to get it to a whole number, to get this to a whole number, I'm going to multiply it by 2 to get it to 3. And what I do to the one side, I do to the other side. So I multiply that one atom by 2 to get 2. So I have 2 atoms of iron combining with 3 atoms of oxygen. So my formula is Fe2O3. Cool, isn't it? Okay. Concentration. If I'm making Ribena, I can have a dilute or concentrated. And yeah, I have a bit of a typo. I apologize for this. So question here, the concentration of a salt solution in gram per decimeter cubed. This is the formula I'm going to use. If they ask about it in grams, I use the mass of the solute divided by the volume of the solution. So I've got 6 divided by the volume, but the volume must always be in decimeter cubed. So I'm going to convert this by dividing it by 100 into 0.5 decimeter cubes. Decimeter cubes is the same as liters. Centimeter cubes is the same as milliliters. So formula, substitution, answer with units. The other way they can ask it is rather than giving it to you as a mass, they give you the number of moles. Okay, so if you don't have the number of moles, if you've got the mass and the relative mass, you can calculate the number of moles and then you can substitute it in. So number of moles divided by the volume. So in this case, we work out from your My Naughty Mother formula that I've got 0.07 moles. I divide it by the volume of the solution, which this time is in decimeter cubes, so I can just put in 0.5 decimeter cubes, and that gives me a concentration of 0.14 moles per decimeter cubed. Now, there's rates on the sheet, there's energy change on the sheet, and there are all the ones that you need for triple science, which are not in this assessment. Look through it, do some practice examples, and I will see you next week. Well done.